This is part 2, okay, I'll call it part 2 of your calculus, the cubic function. Okay, so far you have done the linear function, the quadratic, the hyperbola, exponential, you did the logarithmic function, so you've got 5 functions that you have done so far. Now we are doing the 6th one, which is the last one of the algebraic functions, plus the 3 trigonometric functions, total 9 that you have to. Yes. You did 4 last year in grade 11. Oh, that's yes. Okay, listen. Can you stop talking there? Please be aware that the grade 11 functions are always tested. You understand? Even your June exam. Okay? I'm not worried. I'm going to go over them next week. Yeah. I'll go over them next week. All right. Okay. Let's get on here. Now, the cubic function has the general form ax cubed plus bx squared plus cx plus d. That's the cubic function. Now, this function, it can be drawn as a graph. Okay? If you draw it, there are actually 2 main scenarios. The first scenario is when the value of a is positive. Pay attention, please. Pay attention. If the value of a is positive, the cubic graph will start with a maximum, then a minimum. If the value of a is positive, the cubic graph starts with a maximum turning point, then a minimum turning point. So it has got a maximum of 2 turning points, unlike the quadratic function. If a is negative, it will start with a minimum turning point, then a maximum turning point. Now, if you compare with the quadratic function from grade 10 and 11, right? I'm just going to do a quick comparison here. If you have got a maximum turning point for the quadratic function ax squared plus bx plus c, all right? Here, a will be negative, right? For the quadratic function, a will be negative. Do you remember that? If a is negative, then you are going to have a sad face, right? If you have got a minimum turning point, it means a is going to be positive. All right? And we call that a happy face. Now, with the quadratic function, hey, can you please do me a favor? You know her, and she knows you. There's no need to talk. Okay? Now, with the cubic graph, pay attention. With the cubic graph, it's the opposite of what you have for the quadratic. So, when a is positive, it starts with a maximum turning point. Okay? I'm talking about the cubic graph now. It starts with a maximum. For the quadratic, if a is positive, it starts with a to have a minimum turning point. When a is negative, for the cubic, you start with a minimum, but for the quadratic, when a is negative, you're going to have a maximum. Okay, that's how I remember it. I use the quadratic for me to be able to know the shape of my cubic graph. I used the two. You can decide which way you prefer, right? But be aware that this a here, that is the coefficient of the x squared term, is the one which determines the shape of the cubic graph. The value of a, whether it's positive or negative, determines the shape of the cubic graph. Yes. With regard to that. Okay. The way that I memorize it, can you pay attention? Pay attention. For the cubic graph, if A is positive, right, you start with a maximum. For the quadratic, you have a minimum. So for the quadratic function or the quadratic graph, A is positive, you have a minimum, but for the cubic, you start with a maximum. Okay? For the quadratic, if A is negative, you are going to have a maximum turning point, but for the cubic, you will start with a minimum turning point. So it's the opposite of the quadratic. Okay, in terms of whether you are going to start with a minimum or a maximum turning point. Or you can figure out your way of remembering. But that's how I do it. Right? Because if we ask you to sketch it, you need to know the shape. If you don't know the shape, you won't be able to sketch it. Or if you write down or sketch the incorrect shape, then you are going to have problems. Yes. Will there always be a message? Will there always what? Will there always be a message in the function? Okay. Let me pay attention. I want to answer a question. It's very important. Now, for cubic functions or cubic graphs, they've got a maximum of 2 turning points. There are some cubic graphs that only have what's called, what I would say, maybe one turning point. Okay? I'll talk about those ones, but those are unique ones. Okay? They don't really have like 2 turning points. But the maximum for a cubic graph is 2. Is that clear? Maximum is 2. Sometimes it's not really clear whether we have got both a maximum and a minimum. Okay, I'll show you such a scenario. Yes. I mean, this is not a calculus. Yes. You're still doing calculus. You're still doing calculus. Yes. You have a question? What comes after cubic? We'll do optimization or application of calculus. All right. Can I have your attention? Can I have your attention? Now, sometimes you can have a stationary point. Okay, these turning points, they are also called stationary points in calculus. Okay, turning points in calculus, they are called stationary points because the graph stops increasing or decreasing at the turning point. Okay, so turning points are also called stationary points. Now, there are some cases where you can have turning points or stationary points being what are called points of inflection. So I'm going to talk about that now. Right? So you can have a scenario like this. Okay, this is the most common case. So you have your cubic graph, it starts as an increasing function, then you get to a stationary point or a turning point, then it becomes a decreasing function, gets to a minimum turning point, then a maximum turning point. Right? I hope you remember that if a function is decreasing, the derivative is going to be positive, or the gradient is going to be positive. If the function is decreasing, then the derivative or the gradient will be negative. If it's increasing, the gradient will be positive. Remember, you did increasing and decreasing functions, but in grade 10 and 11, you defined increasing and decreasing functions in terms of x value increasing, y value also increasing. Then a decreasing function, x is increasing, y is decreasing. But now we can define it in terms of gradient or the derivative. So if the derivative is positive, you have an increase in function. If it's negative, you have a decrease in function. So this is the case where the value of A, okay, remember we are starting with the maximum, so the value of A must be what? You see this, the value of A must be positive. It's the opposite of that. Okay? So A here will be positive, and then here A will be negative. So you can also you can have a cubic graph starting as a decreasing function, which means the derivative, you find f prime of x and substitute any value between the turning point and all the values to the left, then you get a negative answer. I'll show you this later when I start sketching. Then if it's increasing, then your derivative will always be positive. If it's decreasing, your first derivative will always be negative. Okay? So make sure you're aware of this. Well, can you please do me a favor? You can copy this later. I need to quickly move to another aspect. Right? Then, now, point of inflection. Right? I've got 10 minutes. Don't write anything. Can you put your pens down? Don't write anything. Now, the point of inflection. Now, it's a totally new concept, which you only encounter with the cubic graph. The question is, what's the point of inflection? It is just a point on the cubic graph whereby the graph changes from being concave, or what we call concave down, or concave up. So the gradient at that point will start to change from being more negative to more positive, or from being, in the case of this one here, from being positive towards the negative. Okay, or it gets closer to zero. But in any case, the best way is just to say the point of inflection is the point where the concavity of the graph changes. By concavity, we are saying there is going to be a change in the gradient. Okay, and that gradient is going to is approaching zero. Okay, so normally a point of inflection is somewhere in the middle, like at this point. So as we move to the right, the gradient of the function will approach what? Zero. Okay? Also to the left of this point, if we move to the left, the gradient will also approach zero. Because remember, at the turning point here, the gradient will be zero. I hope you know that from the quadratic function. So, if the function is concave down, it means there is a local maximum turning point, or a maximum turning point close to a specific point. And in that case, the second derivative, right? Make sure you pay attention. We are going to find second derivative, by the way. The second derivative must be negative when it's concave down. In the region where the graph is concave down, the second derivative will be negative. When it's concave up now, it means that our second derivative, which we are going to find later on, is going to be positive. So the point of inflection, just to summarize, is just a point where the graph will start to change in terms of its concavity. That is, from being concave down, concave up, concave up, concave down. And in that case, we use the second derivative to do the analysis on the point of inflection or concavity. Right? Now, for this one here, it's concave down. By concave down, it's concave up rather. By concave up, we are saying the graph is happy. Okay? It has got a minimum turning point, so the graph is smiling. Therefore, the second derivative will be positive. To the right of this point of inflection, the graph is now set, because there is a maximum turning point. Okay? So the second derivative is going to be negative. Now, this is quite interesting. At the point of inflection, at this point here, the second derivative will be zero at the point of inflection. The second derivative, so if you find f prime of x, then find f double prime of x, okay? And you choose it, and you identify the value of x at that point. You substitute it into the second derivative, you get an answer which is zero. All right? Also here, that's the point of inflection, so f double prime of x will also be zero. Okay. Sometimes, okay, wait. Why do we need the second derivative? The second derivative, it tells us the rate of change. Can you stop talking? It tells us the rate of change of the gradient. Okay? I'm going to repeat that. The second derivative, remember, when you are given f of x, you determine f prime of x. F prime of x is what? Is the gradient of the original function. Right? Then, if you find the second derivative, f double prime of x, it is actually the gradient of the first derivative. So, the second derivative is the rate of change of the gradient. Are you following that? All right. Okay. Listen. You won't get a question on pay attention. You won't get a question asking you to explain what the f double prime is really for. But we are going to use it to analyze the concavity of a cubic graph. You just have to be aware that the second derivative is the rate of change of the gradient. It is actually the gradient of the gradient. Yes. I'll do an example.
So we'll use the derivative the opposites to the they evaluate smaller than
Okay, not really. We'll do questions that maybe can be applied from that. All right. Can I have your attention? Can I have your attention? Can you stop talking, please? As I talk about this, maybe I need to give you an example on sketching. Okay, you will sketch, then we'll analyze together tomorrow. Right? Okay. Pay attention. I've already told you about this part. Can I have your attention? Sometimes you can have a stationary point, which is also a point of inflection. In that case, the gradient will be 0 at the point of inflection. Now, that's a unique case, okay, which generally in recent years has not been tested, right? So you can have the case like this, where A is positive, whereby a point of inflection is also a stationary point. So at this point here, the second derivative will be 0. Also, the first derivative will be 0 at the same point. Okay? This is a unique case, which is the same as there as well. Second derivative will be 0, and the first derivative will be 0, because that's a stationary point of inflection. Okay, I think I'm almost done now. So all I want you to do, wait. When you go home today, just read this, the procedure for sketching the cubic graph. I'm going to give you one cubic function. Try and sketch. You must follow this procedure here. I will talk about it in more detail tomorrow. Okay.